And there's the ding dong that tells me we have started recording. So we talked about plankton being organisms that float and that either don't swim or that can't swim strongly enough to control where they are. Nekton live in the water column, meaning they're not permanently on the bottom, and they can swim strongly enough to control their position in the water. You could subdivide nekton into pelagic and demersal organisms. Pelagic organisms live and feed well away from the bottom. They may never touch the bottom at all, at least not until they're dead or dying. Tunas are a terrific example of pelagic fish, spending all of their time out in the open water. Sailfish, marlin, whale sharks, quite a lot of sharks would all be pelagic. And demersal organisms will either sit on the bottom or hover just above it. Things like flounder and stingrays are perfectly capable of swimming, and they'll move from place to place, but they'll also spend a lot of time resting on the bottom. And such organisms would be demersal or benthopelagic. Benthos, by the way, is the name for organisms that live on the bottom. Benthopelagic, of course, would be kind of in between because they'll rest on the bottom, but they'll periodically swim. So what are our nekton? Cephalopods are a major group of nekton. Cephalopods include squid, cuttlefish, nautilus. They also include octopus, which would generally be more benthic, although some of them are quite capable of swimming. They'd spend most of their time on the bottom. So they might be benthopelagic, but might be better thought of as benthic. Sharks and rays are in a group called the chondrichthyes, the so-called cartilaginous fish. Bony fish, which is most of the fish you'd know, would be in the osteichthyes. And then marine mammals are nekton. Those would be whales in the cetacea, seals and sea lions in the pinnipedia, so-called pinnipeds, and Sirenia, a group you may not be so familiar with of mammals, includes manatees and dugongs. Awesome name, the dugong. And then, of course, if you want nectonic birds, penguins are a magnificent example. Okay, so the cephalopods include 6 living species, all of them tropical, all of them Pacific, I think, or maybe Indian and Pacific Oceans, of nautilus. Cephalopods belong to the phylum Mollusca, which also includes clams and snails and slugs and various others. I guess most of them would be benthic. There's only a few planktonic ones. But cephalopods are highly modified. Instead of a big creeping muscular foot like a snail crawls on, they've got tentacles. And most cephalopods have only traces of a shell, or they don't have any shell at all. Octopus don't have a shell, at least the ones you would know don't. Squid and cuttlefish have internal remains of a shell, and the only one that's got a big external shell left is the nautilus, and this is what a live one looks like. You can see prominent eyes and quite a lot of tentacles, something like 90 in all. Now, if you were to take a shell and slice it, you'd get this. The shell is internally partitioned. You see those curved cross walls dividing up the interior of the shell. They're dividing up the shell into chambers. This is why this is sometimes called the chambered nautilus. And if you look, you can see that the walls are interrupted by this thing that looks like a funnel. Um, those are the septal necks because they cut through the septa. That's the cross walls that divide this up into chambers. And when this critter was alive, there was a strand of tissue called the siphuncle that ran through those septal necks. And what that enables the nautilus to do is to secrete gas into the chambers or absorb it from the chambers, meaning that nautilus can control its buoyancy. They have a new building now, but I used to go every chance I could to the California Academy of Sciences in San Francisco in Golden Gate Park. Really nice place. I loved it. And they weren't primarily an aquarium, but they did have some tanks on display, and they had a tank with live chambered nautilus in it. And it was really weird to watch these guys because they can very quickly secrete gas from their bloodstream into those chambers to make them rise or absorb it to make them fall. So you'd see them kind of bumping along the bottom, and then all of a sudden they just suddenly rise up. It was like, like they'd stepped onto an elevator or something like that. And then they'd, bob along a little bit up at the top of the tank, and then they'd drop back down. And you couldn't see how they were doing it. They weren't moving their tentacles or anything like that. Again, it was kind of like watching them ride invisible elevators. So Nautilus is very good at that. And Nautilus, like a lot of the plankton we talked about, make these diel migrations in that during the day they're down pretty deep, and then they'll rise much closer to the surface in order to feed. I should mention, by the way, you'll see this a little bit better later, but cephalopods in general have an open cavity within the body that they'll pump water into so that it passes over the gills. That's how they breathe. Water goes into and especially out of the mantle cavity through a siphon. And if they contract the muscles of the mantle cavity very quickly, they'll jet propel themselves in the opposite direction. So cephalopods can swim pretty fast by contracting that mantle cavity and jetting water out. And you'll see some great examples of that in a bit. But that's how Nautilus can swim effectively. In addition to going up and down, it can maneuver in the horizontal plane as well. So can spirula. This is an abundant squid in the open ocean. We don't understand very much about them because it's very rare to observe them alive. They're kind of deep down in the water and very far away from shore. So we don't see the living spirula very often. But inside, they've got an internal shell that is chambered like the nautilus shell. You could think of it as being kind of like a nautilus shell that's been evolutionarily reduced, shrunk down. The soft tissues now cover it, but it still has those chambers, and the siphuncle and spirula can secrete gas into or absorb gas from those chambers, adjusting its buoyancy and its level in the water, much like Nautilus does. And those shells do periodically wash up on beaches from time to time. You'll spot them if you spend enough time beach combing. Cuttlefish have a highly modified internal shell called cuttlebone, which you could actually buy at PetSmart or something like that because they're commercially sold as a calcium supplement for birds. If you keep parrots or other birds like that, they need to have something with calcium in it to eat and to chew on, to keep their beaks and their skeletons strong. And you can buy cuttlebone as a calcium supplement, and you put this in your bird cage for the birds to peck. And that's what one of these looks like on the outside, and that's completely covered by the soft tissues of the cuttlefish. By the way, the cuttlefish is an absolute master of camouflage. Although other cephalopods can do this too, squid and cuttlefish have sacs of pigment within their skin, which are attached to muscle cells, and the sacs can shrink to almost nothing or expand to a big dot of color. And this is under nervous system control. So cuttlefish can change their pattern and color to match the background that they're on. And they can do these great colorful threat displays and things like that. They're terrific at it. And like nautilus and spirula squid, cuttlefish adjust the amount of gas in those chambers. That the chambers are a lot narrower than they were in the nautilus, but they're still certainly present. You'd see them if you were to cut that cuttle bone in the right direction. And to fill the chambers with gas, the cuttlefish pumps salt into chambers just outside the cuttle bone. That pulls water out of the chambers because osmosis, and pulling water out of the chambers forces gas to fill the chambers and come out of solution. So the cuttle bone's density varies, and the cuttlefish can ride at particular levels in the water without having to burn energy, pushing itself down into the water by swimming motions, which is kind of a nice trick. You'll note the cuttlefish has fins on either side of the body that it can swim with, that can ripple. It also has that muscular chamber called the mantle cavity that it can squirt water out of in order to jet propel itself. And so do squid. And this squid right here, you can clearly see that pair of highly muscular fins. And the squid can swim pretty slowly, but very efficiently because it's so streamlined. It can swim by flapping those fins up and down or kind of rippling them, as this squid is doing here. The really cool thing is they can swim slowly by rippling the fins. They can swim fast by jetting water out of the mantle cavity. And there's some squid that can force water so rapidly out of the mantle cavity that they can not only jet themselves forward, they can jet themselves out of the water. So they can actually leap out of the water. And in some squid, it gets better than a leap. They will jet propel out of the water, spread their fins, spread those tentacles in the shape that you see right there. They're spread out like that, and there's webbing in between the tentacles. And the fins and the tentacles will actually pick up some lift, and the squid will actually glide. They're capable of gliding up to 100 feet at between 8.8 to 11.2 meters per second. That's roughly the speed of a sprinter. This behavior is not often observed because, first of all, squid tend to be way out in the blue water, away from shore, and they also tend to glide at night, meaning there have been a lot of reports of fishermen who've been out at sea and they've woken up and can't figure out why there's a bunch of dying squid on their deck. But actually seeing them do it is not that common. There aren't that many people that have seen gliding squid. But there has been some footage that was taken. This is from a journal article in 2012, where a Japanese vessel was actually lucky enough to see an entire flight of Todorodes, these gliding squid that we just saw. And they try to calculate, how fast they're going, how far they're going, and use that as a basis of figuring out how efficient gliding is. And they suggested that it might actually be more efficient than swimming when you take everything into account. When you take into account, air resistance and, the amount of energy that has to be burned, gliding may be used routinely on long migrations. It used to be thought they glide as a way to get away from a predator. A predator fish is swimming up to eat you and you just glide out of the water. It may not be perfect, though, because that fish, sorry, that's not a fish. Come on, Wagner. That bird that you see, that's a red-footed booby. And yes, that is what it's called. In hot pursuit of these gliding squid. And so jetting out of the water and gliding might help you escape sharks, but it might put you at risk of attack from seabirds or something like that. So it's an open question as to just how much predation risk is reduced, but it may be a much more common behavior in squid than we think. Incidentally, if you look at some of these gliding squid, you can see that some of them have what look like white threads trailing behind them until they hit the water. That's the jet of water coming out of the mantle cavity. They'll contract that mantle cavity to jet themselves out of the water, and then water will continue to be jetted until the cavity is empty, and at that point the squid will start sinking back. So if you're wondering what that is, and some of those you can see it's starting to look like, the ones on the right are starting to look like a chain of droplets, which is really what that is. But yeah, the ones on the left, it looks more like a thread, but it's just the water jet. So yeah, I hope that is, however your day is going, I hope that's brightened your world a little bit to know that the ocean has squid that can fly. On the other hand, deep sea squid include things like Architeuthis. If you count the length of the tentacles, a squid will have 8 arms, which are relatively short, and then a pair of extremely long tentacles. And in this dead squid, the tentacles are look like they've been broken off. The tentacles are the ones that are bending back towards you. The full length of the squid plus the tentacles can reach 43 feet. There's a squid that's thought to weigh even more, the colossal squid, whose weight might exceed 1,000 pounds. Most of the time, we can't study these because they are deep sea critters and they don't get close to shore unless they're sick or dying or already dead. So most of the deep sea squid that we've ever observed have been dead and in the process of decomposition by the time we get to them. This is presumably what's happened here to this unfortunate Architeuthis squid. There was a case a few years ago where one of these actually swam into a harbor in Japan, and some guy actually scuba dived with it. I'll try to remember to post that footage. It was kind of weird. But that one was probably dying or, not well. There have only been a few cases where we've been able to have cameras in the deep ocean at the right place and the right time to actually spot one of these giant squid. And they're pretty active predators when they're alive, but we have not seen them alive very often. Most of the time when you see them, they look like this. A number of cephalopods, by the way, are bioluminescent. This is a deep sea firefly squid, and those spots contain symbiotic bacteria that generate that light. This has actually been studied as an interesting problem in cell biology. There's a shallow water squid called the bobtail squid, which is fairly common in Hawaiian waters. And the bobtail squid has bioluminescent organs, and they're bioluminescent because the squid has bacteria, but the squid doesn't pass those bacteria to the next generation. So every newly hatched squid has to somehow attract the one species of bioluminescent bacterium that lives naturally in the ocean, and somehow has to get that species to grow in its bioluminescent organs and not the thousands of other bacterial species that are floating around in the oceans. So working out how they do that is an interesting problem. I'm not sure what the current state of the art is, but bobtail squid have been used for trying to understand symbiosis like this. Yeah, bobtail squid, genus Euprimna. Okay, so cephalopods can swim with their fins, but can also go jetting. Many fish, although as we'll see, not all, swim with their tails. Fish in general generate thrust by pushing backwards against the water, much like you paddling a boat. Every time you put in your oar and you push water backwards, you push yourself forwards, because for every action there is an equal and opposite reaction. So over here, this is a top view of a swimming eel, and the eel is bending its body into these S curves, and whenever part of its body pushes backwards or pushes backwards at about a 45-degree angle, the fish is thrust forwards at the equal and opposite angle. So this fish will be thrust forwards and to the right, and then as it bends its tail in the opposite direction, it'll be pushed forward and to the left, and alternate being pushed forward to the right and forward to the left. Kind of like Axl Rose in the Sweet Child of Mine video. Not that you know what that was, you post-millennials. Okay. Most fish that actively swim use BCF locomotion. That's body and caudal fin. The caudal fin is the tail fin. And this is how they generate power. If you look at over on the left, you're looking at top views of swimming fish, and fish that swim like eels use what's called anguilliform swimming. Anguilliform means shaped like an eel. Duh, you probably knew that. And most of the body is in motion when an eel swims, and the head swings back and forth like a pendulum. You know, the entire body is being thrust into these S shapes, and the head goes back and forth. If you look on the right, thuniform fish. Thuniform means shaped like a tuna. The head does not move very much left to the right. The body is mostly stiff, and pretty much only the tail is the part that's lashing back and forth. So thuniform fish have fairly stiff bodies. They don't sway their heads back and forth, and the work is done by the rear part of the tail and the tail fin. And then in between the two, chorangiform locomotion is kind of that happy medium. The body is not flexed as much. The head, it's not flexed as much as in anguilliform, but it's not quite as stiff as in thuniform swimming. And the head doesn't move quite as much as anguilliform, but more than chorangiform. Okay, so chorangiform is kind of in between. And here's a thuniform fish. Thuniform means shaped like a tuna, and that's apt because this is a tuna. That is a bluefin tuna, and you can tell it's built for speed. You can see that the body shape is extremely streamlined. You can go back and look at that, optimal, low drag design that we talked about a couple of lectures ago, and you can see that this thing is very close to it. And if you look at the tail is high, but it's narrow, and that means a tail that this fish can flex back and forth with relatively low drag. If it was a wider tail, less narrow, there'd be more drag on it. This is a drag minimizing shape right here, this high, narrow, crescent shaped tail. And this is because tunas are built for cruising. They swim fast, they cover a lot of distance, and they do it with great efficiency because they've got this crescent shaped tail that can generate a lot of thrust with relatively little drag. We can actually pin some numbers on this. You can take a tail, or for that matter, this works with a wing, or a any fin, any airfoil or hydrofoil, any wing-like structure, and calculate its aspect ratio. And the aspect ratio is you cube, or you don't cube, you square the height and divide it by the surface area, which gives you a dimensionless number. And as you can see on the top, that's a tuna. The square of the height is the area of that square that's been drawn on top of the fish. And the surface area is, of course, the black area where the actual tail has been shaded in. And you can see that that square is much bigger than the actual tail. So the square of the height is larger than the surface area. So that aspect ratio is about 7.5. On the other hand, if you look at that bottom-dwelling goby, that fish down there, B, Pomatocystus, the square on top of the tail represents the square of the height. The actual tail is bigger than that square. So the aspect ratio here is less than 1. And high aspect ratio tails are correlated with efficient cruising. You can actually do the same thing with airplane wings, by the way. Airplanes that have to stay aloft for very long times and fly very efficiently tend to have very high aspect ratios, which means very long, narrow wings, like gliders, for example, or those drones that were flying. Those might have to stay overhead for many hours, and they don't have infinite amounts of fuel. So those wings tend to be very long and very narrow. They're very high aspect ratio wings. Whereas a plane where efficiency is not the goal, but speed and lift are the goal, are going to have lower aspect wings. I'm thinking of, carrier fighter jets or something like that. And the same basic math applies to fish. Fish that hunker down on the bottom, though, that don't do a great deal of cruising, demersal fish, right? The ones that hang out on the bottom. If you're hanging out on the bottom, especially if it's a very rugged bottom like a coral reef, like this copperband butterfly fish, that's where that lives. In that environment, you don't need to cruise. You're not trying to swim efficiently because you're not going to be swimming very long distances, because if you do, you'll crash into something. What you need if you're demersal is maneuverability. And so butterfly fish swim primarily by using the pectoral fins. And if you forget what those are the fins that are sticking out on the sides just behind the gills. It's actually really hard to see the pectoral fins in this picture because these fish are the pectoral fins are transparent. But you can just see them kind of back of the gills. Okay, there's a copper-colored band that cuts through the eye, and then the second band is where the pectoral fins start, and they're covering or they're lying over part of the third band, if maybe you can see them now. And they'll use these for stability. In fact, all fish will, just to control their stability in the water, but they'll use these pectoral fins for propulsion as well as for stability. This is the kind of thing you could see if you were to go over to Pet Country or Petco and look at their saltwater tanks. A lot of the slow-moving coral reef fish that are so pretty use this type of locomotion. It's called MPF, median paired fin locomotion. But then, of course, if you scare this thing and it makes a burst of speed, it'll switch over to swimming with its tail. So a lot of fish will use median paired fin locomotion at low speed and switch to body caudal fin locomotion at high speed. And there's some fish that do cruise efficiently using their median paired fins. And this is one. This is a manta ray. And the manta ray's pectoral fins are continuous with its body. And by flapping them up and down, manta rays can swim through the open water and even jump out of the water occasionally. Manta rays will occasionally breach, push their way out of the water and catch a little air before they crash back down. So median paired fin locomotion is often associated with maneuverability instead of speed, but the manta ray can actually use its median paired fins and pick up pretty good speed. And you'll notice that the aspect ratio of the manta's pectoral fins is relatively high, right? Long and narrow relative to surface area. If you compare that with the Caribbean electric ray down there below, that's a demersal fish that spends most of its time sitting on the bottom, grubbing up clams and things like that, and not usually swimming very far or very fast. That one has much broader median paired fins, right? The body basically looks like a circle. The manta ray has much longer and narrower median paired fins. So that aspect ratio thing works again here. That having a high aspect ratio and longer, narrower fins is associated with efficiency at cruising speed. Fish that don't cruise don't have to have that. Incidentally, a few years ago, we went to Florida with some of the family, and it turns out that in the waters off of, where were we? Off of the island where we were staying, there were actually a fair number of Caribbean electric rays. And if you touched one, you did get a bit of a shock. Not a really major one. It was just a little tingle. But my brother-in-law got shocked several times before I could explain to him what was going on. And hey, sorry, I've got a cat on my keyboard. Hello, cat. There, as we were. Yes, hello, you annoying cat. Yes. I'm sorry, these aren't catfish. Okay. Now, we saw in cephalopods how some of them can control their buoyancy with gas-filled chambers in the shell. Most fish, with the obvious exception of sharks, can control buoyancy using an organ called a swim bladder. Swim bladders actually evolved from pouches off the gut, and there are a few fish that retain an opening between the gut and the swim bladder. So if you look at, all of these, sturgeons, climbing perch, beach ears, those are mostly freshwater. Gars and bowfin, I presume you know gars and maybe bowfin because we get those in Arkansas. And then various lungfish, they retain an opening between the gut and the swim bladder, and they can gulp air from the outside and force it into the swim bladder. This, by the way, is also the evolutionary origin of land vertebrates' lungs. Your distant fishy ancestors had this open swim bladder that they could use to control buoyancy and use as a breathing organ. And now your lungs have become very highly specialized as a breathing organ. There's some marine fish that retain a connection between the gut and the swim bladder. That's called being physostomous. Herring, if memory serves, still retain a connection between the swim bladder and the gut. But most bony fish have lost that connection between the gut and the swim bladder. The swim bladder might develop as a gut pouch when the fish is an embryo, but the swim bladder will pinch off and become just a separate gas-filled structure in the body that's not connected with the gut. Fish like that are called physoclistus. And fish like that, since they can't gulp air and pump up the swim bladder or burp air to get rid of it, they'll secrete gas from the circulatory system into or out of the swim bladder using a capillary network called the rete mirabile, which is Latin for marvelous net. And so gas can be secreted into the swim bladder or absorbed and taken out of the swim bladder, and the fish can rise or sink without having to spend muscular energy in pushing itself up or down. Sharks don't have a swim bladder, and sharks have to swim in order to stay in the water. If they stop swimming, they'll sink. Sharks get an assistance from those pectoral fins, which can generate a certain amount of lift. So sharks can stay up in the water in the same way that airplanes can stay up in the air, generating that lift. But sharks also have a nice trick. They've got huge livers. I've dissected sharks before, and an awful lot of the space in the body cavity is just this giant liver. And the liver is very rich in oils, notably a very light, low-density hydrocarbon called squalene. And you can see it is less dense than water. It's 0.85 grams per cubic centimeters. And deep-sea sharks may be very oily indeed. Squalene can make up 15% of the total body weight. So sharks are relatively low density for their size, and that's a nice trick to increase their buoyancy. I think I typed decrease, I meant increase. Sorry about that. They'll increase their buoyancy with that large, not very dense, oily liver. I should mention that these days they're promoting shark liver oil as a dietary supplement. Here's some capsules you can get that will supposedly extend your life and promote immune system function by taking these dietary supplements of Norwegian shark liver oil. As far as I know, there's no medical evidence that it really helps. Your body is perfectly capable of making squalene. You've got it in your skin oil and your hair oil. Your fingerprints contain squalene. There is some concern that fishing deep-sea sharks for their livers is putting stress on vulnerable populations. As we'll see, when you can't observe a population very easily, it's hard to tell what effect you might be having on it. And deep-sea sharks may not reproduce fast, but they live very, very long. They found some Greenland sharks up in the North Sea that are suspected to be over 200 years old. This would make them the longest-lived vertebrates, longer than Galapagos tortoises. And a population like that grows slowly isn't going to recover very fast. And overfishing deep-sea sharks could put real stress on populations that can't rebound quickly. So I'm not going to tell you what you may or may not put into your bodies, but I'm going to recommend that you not take shark liver oil capsules. That's potentially bad for an ocean population. And as far as I know, it doesn't actually do you very much good. There's all kinds of supplements marketed that are supposedly good for your immune system, but probably don't do that much good. And I will stop recording now.